is Etienne Guichard. I was a student assistant under Stefano, who's here with us, where we did two papers together, one on EngramNCA and one on ARC-NCA, which was leveraging our EngramNCA method for solving ARC problems. Um, Apart from that, I did a master's in cognitive robotics, and hopefully I'll be a PhD student of Stefano's in a short time. Stefano, if you would like to say
Yeah.
something.
So first of all, thanks for the invitation, Nel and Michael. My name is Stefano Nichele. I'm professor in computer science in the machine learning group in a rather small university college in Norway called Østfold University College. Sorry? Oops, just noise maybe?
Yeah, I
Yeah,
think
that
someone
was a mistake.
accidentally joined.
Yes. I'm, as I said, I'm a part of this university college called Østfold University College. It's a very nice place on the south coast of Norway, so you're welcome to visit anytime. And I just moved in a new house yesterday, so it's a bit of a mess around and carpenters coming in and so forth. So unfortunately, it's not been possible to prepare a presentation myself for today, but Etienne is leading it, so that's great, and I'm here for a discussion. My background is in computer science, as I said, but I've been interested in the basically evolutionary developmental systems from a computer science perspective, so artificial systems, but therefore I also have a strong interest in biological systems and how can we take advantage of developmental processes coupled with evolutionary processes for basically artificial systems, robotics, and AI. I also been working with in vitro neural networks, where basically I have not been doing leading any lab work. We have colleagues in neuroscientists that grow the neural networks in vitro, but we develop basically the kind of interfaces and kind of data analysis. So we have been trying to develop some kind of closed loop system where we interface with neurons and we control maybe a robot or maybe do some kind of classification tasks or regression tasks and try to train the biological neural networks to a certain behavior. We have been also interested in analyzing over the developmental time, extract some kind of connectons from those networks to see what's kind of so it's not topological connectons, but it's functional, or it's basically based on correlation on electrode activity, and then study the networks that we obtain with more theoretical network science methods. And of course, I've been very interested in cellular automata of all sorts because they provide a very nice sort of abstraction for many developmental processes. And recently, we have been working also with neural cellular automata, initially using neural evolution methods for training the neural networks, and now also for convenience, also using gradient descent methods for training them. And I mean, a lot of the work that Etienne will be presenting today is inspired by your lab's work, and especially in these ideas of regrowth of organisms, and also the bioelectrical processes happening, and also with the kind of inspiration from the computer science perspective from computation, and what is computation and where is computation done, and kind of Turing machines, and how can we see biological processes as this kind of computations that we can associate with Turing machines in computer science. So I hope that you will enjoy. I will be here also for the discussion and answering questions, but I leave the floor to Etienne.
Yes, thank you. It's less of a lecture and more just like a presentation on our method as well. Please feel free to interject at any point if you have any questions or you want anything clarified. I really don't mind. So the first part will be on EngramNCA, and then, like I said before, the second part will be on ARC-NCA. The deployment of our method on solving ARC problems. So let's get started. Oh, there you go. And I don't know why I clicked twice. Okay, so the idea was to move from a NCA or a CA parameter equals CA genetics point of view with neurocellular automata, which was sort of the previous view, to a CA parameters are the world physics. And to do this, what we did was train one CA to learn computational primitives or the physics, and then train a second CA to exploit those primitives for a more complex task. Another view is you can see the CA as a Turing machine, as Stefano was saying, with a neighborhood, and the tape as the program to this Turing machine, where the secondary CA learns to change the program. So what we do is, in standard cellular automata, you have an RGB alpha channel and then a bunch of hidden channels that are used for the CA to store hidden information that it can use for computation. So we chose to take an arbitrary length part of those hidden channels and just turning it into static encodings. The CA has no access to them. It can just see them, but it can't write to them. This can encode simple shapes, as you can see on screen, or even more complex parts. So sort of the classic NCA growing shape is this lizard. And so you can like chop up the lizard into its constituent components and encode each one of them into the CA encoding channels. We chose to do this in a binary encoding way. So you need n number of primitives to the power of 2 minus 1 channels to encode them. So it's not quite one hot, but it's also not leveraging the continuous potential of NCAs. But yeah, this was mostly an arbitrary decision. Like I said, there's two CAs. We called the first one gene CA, so this is the one that's conditioned on the genes. It works like a standard NCA, so you have the N channels, RGB alpha, all the way to the encodings. They're read by a convolution filter. They're usually set. This is Sobel, X, Y, Laplace, and an identity. And then the output of these filters are passed to a feed-forward neural network that produces an update vector. The difference for us is that our update vector is only partial. So we only modify the states that are allowed to be modified, and then we append the gene channels to the end after the stochastic updates. Again, this means that the CA becomes conditioned on these. The second CA is the gene propagation one. It is effectively the same CA except reverse, so that it only has access or write access to the gene channels. Everything else it can't see. So you could also see it as a way as the two CAs are conditioned on each other. One of them writing the tape conditioned on the output, and one of them giving an output conditioning on the tape. And then the entire EngramNCA is an ensemble, so they operate sequentially. You have your state N, you pass it to the gene CA. It creates an intermediate update of just the non-gene channels. You pass that to the gene prop CA, it creates an update or the full update to the gene channels, keeping also the intermediary update. So you have the full state update at N+1. For the training, the gene CA uses a multi-batch training process. So this is for every primitive you want to encode, you need a separate pool. Just a quick question, does everybody know how NCAs are trained? Or do you want a quick explanation?
Please give a quick explanation.
Okay. So NCAs are usually trained on, or at least the classic growing NCAs paper and variations of it are usually trained on sort of a single problem. So like a morphological growth problem, like growing a lizard, like in these images here. And they use a pooling method for sort of infinite horizon time. So the CA is trained for a certain amount of steps, and then on a seed, and then the output of that seed is added back to the pool, and then resampled from that pool with always at least one of the samples being the original seed, so you don't get catastrophic forgetting. This is to allow for long horizons, since you can't, with backpropagation through time, if you train for like 128 steps, your memory requirements grow as the steps grow linearly, so n steps. so it becomes very expensive if you want really long horizon training. So instead of what you do is you truncate it. So you do a portion of those end steps and then you add it back to the pool and you resample from the pool, restarting the gradients at a later stage. What this also allows is for exploration around the state space, since at the very beginning it makes a lot of mistakes. And then it has to recover from those erroneous states that it has arrived. This sort of adds to the robustness of it all. So that's the classic training method. So what we do here is for every primitive you want to encode, so usually it's just one, you just instantiate a new pool. As long as the primitives are all the same size, you can just sample from the pool. So if you have a batch of, say, 9 and you have 3 primitives, you can give each primitive 3 members of the batch. So yeah, the way you train them, you sample from the pool, you concatenate them into a batch, you run the end step updates. This is all conditioned on the genes. We then use L2 loss, so on the image, so this is just pixel-wise loss, and then update each pool based on the output of the gene CA. The gene prop CA is very similar, except now we have a gene CA also affecting the gradient flow. The gene CA is frozen, so its weights are not updated. So it's just the orange arrows here only affect the gene prop CA, but it's effectively the same method. You sample from a pool. Okay, my touchpad is very sensitive, sorry. You sample from a pool, a set of starting states. You do n update states. In this case, the steps are the two updates, the intermediary update and the full update. For n steps, you get a result, you do L2 loss on it, you backpropagate, and you append back to the pool to sample from. Uh, a quick note on pools, they do actually affect how the training happens. So with larger pools, you start, the pool is initiated with just a starting grid. So with very large pools, you see the starting state many times. So the NCA will learn to sort of stabilize the starting grid very well, but it'll take longer to train for the final image. For smaller pools, you tend to have a faster training, but you can get an effect that's called pool poisoning. This is where there are so many erroneous states that comprise such a large portion of the pool that it's, or erroneous irrecoverable states, that the pool over time gets poisoned with just irrecoverable states and learning halts. So it's sort of a balancing act with the pool. So some of our results, this is the first interesting results, is that you can actually encode multiple shapes into one CA. The previous methods could only ever encode one and would need to retrain or have basically a pool of CAs for each shape you wanted. In this case, now because we have like conditional learning on the genes, you can now just teach it to grow different shapes based on the genes, or i.e. we've trained it to have a world physics and then a way to exploit that physics to do different things. We also got some interesting untrained behavior. You can now mix the genes and you get sort of an intuitive mix of what the shapes would be. So if I go back, you have a blue square, a green circle, and a red triangle. And if you mix the genes for a blue square and a red triangle, you get this weird mix of a shape, and the same for all of them. And this was not trained. This is not something we expected to happen. We just tested it and it seemed to appear. Uh, Another one, which is sort of nice compared to the original method, is individuality. So you get these strong boundaries um, based on the conditioning. And if you ever play with the original NCA, if you try and put two lizards together or two of one shape together, they'll just start mixing and you have a total loss of the shape. Whereas here, there is some mixing. Obviously, it's not perfect, but you have some boundary conditions. Uh, Now, what the interesting thing is, what can we do with these encoded sort of shapes? Well, we can now change the secondary CA to grow something more complex, sort of a combinatorial problem style, where how do you combine like three shapes with three very basic colors into a more complex shape? So on the left, what we have is the gene CA is trained just to regrow the lizard body parts. So these, so each encoding is a single lizard body part, and then here it's trained to regrow the whole lizard from those gene encodings, uh, effectively stitching the body parts together. On the right, where the quality is less, the GeneCA is trained to grow the different shapes, just very basic shapes, and then sort of mix those shapes. So that's a more complicated mixing. And what you see are two different starts. See if I can, there you go. Uh, so it was trained to grow the lizard from the blue square and only the blue square. So what is nice as well is that if you try and grow it from, say, the green circle, it won't grow. It will just dissipate. You can also do hierarchical embedding. So uh, basically the same thing we did with the gene CA, where we have unreadable channels, but now there's also an unreadable channel for the gene prop CA. So it can't, oh, sorry, not unreadable, unwritable channel for the gene prop CA. So you can sort of keep stacking these embeddings. So now this CA, what it does is it can grow the different shapes, the circle, the square, the triangle. You can also grow a lizard, but you can also prompt it or tell it to grow a butterfly. And you can effectively do this ad infinitum as long as you have a large enough CA. So the more shapes you want to store, obviously, uh, uh, the more parameters you need. Not for the gene CA, but for the gene prop CA. For the gene CA, you just need the amount of parameters needed for the primitives. Another interesting thing we found was generalizability on movement. So on the left, we have a linear system. This is a very famous CA by Bert Chan. A continuous CA. It's not perfectly local, so the difference between this and a neural cellular automata is that the neighborhoods are larger than just a 3x3 more neighborhood, and they can be honestly arbitrarily large. I think for this specific shape that you see, it was um, a neighborhood of 31, so that's 15 on either side of the central cell for sensing. Um, And the question was, could you replicate the dynamics of something that has a larger neighborhood with a 3x3 more neighborhood? With a classical NCA, the answer is no. It's effectively just learning the video. The training is just on 500 images of the video sequentially. And after those 500s, you have total deterioration. Whereas with the the Ngram NCA, um, it extends the horizon at which it can do it. You basically teach the gene CA to grow the initial primitive and the gene prop CA to move it. And although the generalization is not perfect, it is better and it has a longer horizon. It doesn't actually deteriorate. You can just let this run continuously, just like the Lenya. So conclusion, we can train many behaviors. Uh, in one model of an NCA, which was novel behavior. We can train separate NCAs to exploit those behaviors for more complex tasks, and the model presents desirable untrained characteristics such as out of training generative capabilities, strong untrained regenerative capabilities, and strong boundaries between behaviors. Uh, Especially the strong boundaries between behaviors, it sort of suggests that you could build models, computational models, where you could cordon off sort of computational regimes or computational primitives and have them still talk to each other, but without them interfering with each other. All right. Well, that was the first one for uh, the EngramNCA. Are there any questions?
Can I ask a question about so you have a figure show you in one grid in one space you have multiple different shape. Yeah. Uh,
Yeah,
so so how do you control the gene? Because you are you controlling at pixel level or just a single
yeah,
pixel?
yeah. Single pixel at the center of the shape.
Oh,
A single pixel gets encoded with the gene at the center of the shape. Um,
and does this gene propagate or you
no,
just
it does
control
not.
that one?
It does not propagate. No. Um, The initial pixel can see its own gene information, but all neighbors will not be able to see that gene information. So the propagation has to be done within the hidden channels that are writable by the gene CA. So it has to sort of implicitly propagate the gene information.
Interesting.
Um,
So for the linear example, how because it's moving, how do you control that?
yeah, so That's the gene propagation CA. That one is allowed to propagate the genes. So this one, the gene CA is just trained to produce the first image of the video statically, and then the gene prop CA is trained to move the genetic information in such a way that it produces the linear system.
Okay.
So that one it
So
can propagate.
yeah, so does this propagate is being trained to be so? Do you like force it to do so, or it naturally doing this
It naturally
propagation?
does this. It naturally,
Well,
yeah, yeah. It's implicit in the task. So, uh, yeah, I wouldn't know how to describe it, but basically, it's trying to do it's back propagation. It's implicit in the task. It has to learn how to propagate the genes. So obviously, it could learn to do nothing, and then you have a really bad loss, or it can learn to propagate them and then do
interesting.
interesting things.
Yeah, thank
On
you.
the single pixel gene thing, this is why I think at least we have these strong boundaries. Somewhere in the implicit information propagation within the like writable channels, I think that the shapes sort of encode distance to the center. And by encoding that distance to the center, I think it also encodes a boundary into the shape. And so this is why you get this sort of individuality
Oh,
behavior.
yeah, interesting. Yeah, thank you.
Yeah.
Can I
I
just
And
also
jump in? Can I just
yeah,
jump in just to kind of clarify a super basic thing here? So the first NCA, the first sort of neural network is trained from a single seed placed in the grid, which has kind of the genetic information, the encoding of what shape it should grow. It's just trained to grow that shape without being able to propagate the genes.
yeah,
It's just training basically the first NCA that is just growing the shape, the primitive shape. And so one does this for if one has multiple primitive shapes, can do this with multiple primitive shapes, each with their encoding. Those encodings, those genetic encodings are not propagated. It just learns that from that very seed with that genetic encoding, it should grow a shape. That's the first NCA. Then one this is in place, then one can train the second NCA, the one that propagates the genes. And that one is basically working in tandem with the first NCA trained to grow the shapes. So the one growing the shapes is producing kind of the primitive shapes. The one that is moving the genes is then able to grow more complex morphologies, relying on the basic primitives that were trained, just by being able to actually propagate the right genetic encoding in the right places, so that it activates the primitives in the right place and in the right time. But it does not change the growth of the primitives. It just relies on them. The weights are frozen when we train this second one. It just learns to basically propagate the genes in a manner that is also matching and mixing the different shapes in different places and in different times, such that you obtain the larger morphology. And for the linear example, that's quite interesting because there you train the first NCA to basically grow the first image of the glider, and that's kind of then remains untouched, that then remains unchanged, and that's all it knows. It just to learn to grow that very specific kind of image, and then the second one is just learning to from this image to propagate the genes to the neighborhood such that it modifies it at the next frame. Right. So, but the first NCA is able only to learn that to grow that very image that was trained, and the second one is not changing it; it's just propagating the genes. So, in fact, when you have seen this kind of a training method, one CA is just taking the genes and appending it at the update step. Those are not written by the neural network. On the other hand, the gene propagation CA is not updating all the other channels of the CA. It's just appending the updated genes. The neural network is just responsible for updating the program, basically. This kind of tape in the. I hope
yeah.
that it clarifies a little bit.
I guess a more computational view as well of this would be if you assume the NCA is a Turing machine, then what we have is a Turing machine that has learned or that can solve a single problem based on a program. and then another machine, doesn't have to be a Turing machine, but another component that has learned to basically deduce the computational regime of the Turing machine and produce tapes to get desired behavior. It's effectively looking for programs to get desired behavior. It's obviously a bit more complicated than that because we're using neural networks, and you're not sure if they're Turing complete or what programs they can represent and all of this. But uh, you could see it like that effectively, just a Turing machine that has executed a single program really well, and a Turing machine or a machine that has learned to produce programs to exploit that Turing machine's behavior to do anything else.
I should
Maybe
also
I
add, I just wanted to add one interesting fact that you can stack those NCAs, as you have seen in this example, growing like two different complex morphologies like the butterfly and the gecko. Here we have like basically three layers. So you can stack it up such that there is one extra sort of layer that is able to use, or just to say there is one first step that is growing the basic morphologies. And then from those basic morphologies, you can encode different shapes like the lizard and the butterfly. And then you have another one that controls which one of the two should be activated and should be grown. So you can stack up layers. Now we have tried up to 3, but one can stack up to even more than that, basically.
maybe I missed something. Maybe you mentioned it. You said that the gene encoding of the image is only encoded in the seed itself, and
Yeah,
the
so
other cells doesn't see it.
correct. Yeah, the other cells aren't seeded. So when you start, okay, let's see if I can get here. When you start, trying to grow the shapes, you start with a single pixel that has the genetic information.
Right.
And
So,
that pixel will be the only one to ever have the genetic information.
so what happened in the moving part? You move also the seed, or
Well, uh, so in the moving one, it's not us that's moving it. It's the gene prop CA that's moving it. So we've
okay,
basically trained the secondary CA to say, well, here you have an image that has a seed that grows, or sorry, here you have a CA where when you give it a seed, it grows an image. We now want you to move that image so that it looks like this linear system. And so it has learned some form of complicated dynamics to move that seed and change maybe where that seed is represented or if it's spread out, so it can change the shape as well over time.
so the gene prop
Could you
CA.
go back? Sorry, Etienne, could you go back to the image where you show the architecture of the gene prop CA? Because the gene prop CA, if you look in this image here
Yeah.
carefully, you can see that the 16 channels representing the actual visible image, so the RGB alpha and all the hidden channels there, those are basically not updated by the gene prop CA.
No,
The
it
gene
only
prop CA
produces.
steps is just taking the neighborhood of that cell and it's updating its own kind of genetic encoding to what is needed for the next step. And is taking the other 16 visible channels, or like visible plus hidden channels, unchanged, unmodified, and appended there. So one update step of the gene prop CA is in fact just copying the first 16 channels they are, such that the actual behavior is unchanged. That's done by the previous CA. That's the update set of the previous CA. This is just responsible for updating the program such that basically mixing the genes such that the next step it will utilize the useful part of the kind of the right update from the learned pool, and it's kind of propagating to the next iteration the genetic encoding needed for the next developmental step.
Okay, so in case of linear, I guess if you have interaction between creatures, so
Yeah.
that network need to learn that kind of interaction.
Yes, it would be the gene prop CA that learns the interaction. Yes.
Okay,
Yeah, the gene CA only would store basically the first frame. This was done sort of in uh how do you say it again? Curriculum learning style. So it was fed a video basically, but the backpropagation was first done on the first 10 frames of the video accumulated, and then once the loss was good enough, it was done on the first 20 frames accumulated, and so on and so forth. So it was effectively learning to replicate a video. What was interesting about it is a traditional NCA basically learned the video and the video only, and any time step after that was catastrophic. Whereas the gene prop CA sort of seemed to learn some underlying dynamics of Lenya, because Lenya has underlying dynamics to it, as sort of a shortcut to sort of optimizing for that video. And then when you let it run for longer, it was actually fine. It wouldn't just disintegrate. There was some stability in it compared to a traditional NCA.
Can I ask a last question to be absolutely sure what's going on?
Yep.
Because you mentioned you're using binary genes, right?
Yep.
The gene prop CA is not restricted to binary outputs. So
No,
it's
no.
something
It can,
implicitly learned during training, and then from the single seed cell, which is binary, the rest will grow as the NCA learned it, basically.
yeah. So yeah, seed cell
Okay.
binary. The gene prop CA is not binary. If you actually look at, say, this one here, so encodings are 0, 1, 0, 0, 0, 1, and 1, 0,
So that's
0
a
for
seed
these three
cell.
shapes. That's the seed cell. So now the encodings are 0, 1, 1, 1, 1, 0, and 1, 0, 1. So this is the mixing of the genes that you can get. You can imagine that if here you get purple, because this is, red and blue. You can imagine that if the gene prop CA wanted like a blue or a purple, it could effectively do 0.51. So it can use floating points. And actually, if you do use floating points, the interesting thing is you can get like smaller shapes, or I mean, the behavior really depends because every time you retrain a neural cellular automata, you get slightly different behavior. But effectively, you can get smaller shapes or slightly different colors. So even though the encodings are binary, the neural cellular automata is still acting in a continuous space. It's just that the target is on a binary encoding. But if you give it something less than binary, or like something in a continuous space, it just sort of guesses or does something anyways that is usually quite a good approximation of what you would expect.
Yeah, this is super nice. Maybe one brief other question or two. How more intensive computation-wise is the training? And are you training it in tandem, like iteratively, or you're pre-training the gene NCA and then after that the gene prop NCA, or some tandem training to improve them both iteratively somehow?
So for in terms of the single CAs alone, it obviously just depends on the complexity of what you're trying to encode. The single CAs are about the same size for training as a normal CA, so they're not expensive to train. This was done on a 4070 Ti at home, and to train this behavior, it takes about like 2 minutes. They're really tiny networks. We're talking from 10,000 to 100,000 parameters at most. However, you have two CAs running together, so you do eventually get a larger sort of gradient accumulation in this step. Where is it here? So for the gene CA, the training is effectively the same as any other NCA. It's just dependent on the complexity of the shape you're trying to grow. The pooling method doesn't add anything else. I mean, if you're going to use a batch of 9 anyways, you still have a batch of 9. It's just the batch is split between 3 different shapes with 3 different encodings. For the gene prop CA, the gene CA is frozen, so the weights are not updated, but they do contribute to the gradient flow. Thus, it does get about twice as expensive to train. It's not expensive still, anyways. These are tiny networks, and they still train no problem on a 4070 in I think it maybe took 10 minutes for this part, but yeah. And the refinement is only done to the gene prop CA. So once the gene CA is trained, that's it. It's frozen forever. And so any improvements you get are from training the gene prop CA to the final results.
Okay. Do you think it would make sense at all to train them like in tandem and incrementally?
We'll actually get to that in the next part.
Okay, cool.
So if you're all okay, I'll start on the ARC-NCA part of it. So a little preface to this. Sort of the idea came from the results on the mobile morphologies and how there was at least some stability or some generalization. And Stefano basically thought what if we could apply this to ARC problems since they require heavy generalization? And so
And if I can also add,
yeah,
we thought that this shouldn't work because there are too few examples also.
yeah.
So the idea was like just try, but this shouldn't work in principle because you cannot learn this kind of dynamic behavior from 2 examples, 3 examples. Yeah.
So introduction, a quick recap on ARC. ARC is the abstraction and region corpus. We did ARC-AGI 1. ARC-AGI 2 and 3 were not out when we did this paper, but came out just as we published it. So I have to clarify, it's AGI 1. It is a reasoning benchmark, few-shot learning. So machine learning systems get about 2 or 3 examples, like Stefano said. It's quite simple for humans. It actually uses a lot of human priors, such as our ideas of physics and of how things grow. It is very hard for current machine learning techniques to get anything competent on. It's a grid-based problem, so it's grids. ARC-AGI1 are grids 30 by 30 maximum with 10 states, and machine learning systems get 2 attempts per problem, so they get to do 2 shots at it. So it's hard for traditional machine learning, mostly because traditional machine learnings learn mappings, and mappings tend to be quite ineffective for reasoning. Reasoning is a continuous process that has to be done in multiple shots, and a mapping is usually a one-shot attempt. These mappings require huge amounts of data to train, and in ARC-AGI you get about 3 examples, which is very small. And models with enough human priors, so LLMs, which are the ones that tend to do well, are hugely expensive. So you usually wouldn't do this at home with an LLM. You require OpenAI grade equipment to be able to get a good score with an LLM. So a little bit on the potential of neurocellular automata. This is on the technical side first. So they're small but expressive. Again, they're cellular automatas. Cellular automatas are or can be Turing complete, can express themselves in any other arbitrary computational system. Neurocellular automatas are a subset of all CAs possible. They generate their own training data, and I actually wanted to touch on this more. If any of you have been following ARC news, there's a paper called Hierarchical Reasoning Machines, HRMs, that's purported to get about 40% on ARC with 29 million parameters. The ARC-AGI Foundation did a bunch of tests and effectively found that the architecture had nothing to do with that score, and it was more about how they trained, how the HRM had multiple shots, and it got to see multiple. Basically, I got to see a sequence of it improving on the on its own output to try and refine the output and all this. And this is effectively what NCAs already do with the pooling method I described previously. So accidentally, just by the way we train NCAs, we already found sort of a very good way to train for ARC problems. Again, they're trajectories, recurrence over mappings, and the states affect the computation. So they self-modify their own state on the forward pass. They do have the potential for gradient-free meta learning. We're nowhere near that yet, but I do think it is a potential. Then on the practical side of why NCAs, they're already formatted as a grid, so it's sort of easy to transpose ARC problems onto them. They're used to simulate biological phenomena quite often, and this is relevant for a lot of ARC problems. They're cheap and fast to train with backpropagation, and it was novel and unexpected, unexplored. We just wanted to see if it could work. So we took, or in our paper, we tried 4 models. There's 5 here, but Ngram v2 we never use in the end. A standard NCA, so this is just the standard Mordvin et al. NCA to grow shapes, and then 3 versions of EngramNCA, what I just presented. One which is just a standard, what I just showed you, and then one with improvement called sensing and toroidal. I'll talk about this in a minute. And another one with an improvement that was sensing toroidal and local versus global training. So the augmentations, in standard NCAs, the convolution kernels are static. They're the Laplacians, the Sobols, and the identity. And here, for the sensing, what we did was allow the learning, the convolutions to be learned, except for the identity one. But yeah, it was allowed to learn its own sort of sensing kernels. The toroidal bit, standard NCAs are toroidal. They're sort of positionally invariant. You could grow the shape wherever you want. It doesn't really care. For some arc problems, this is actually a very bad thing since you need a hard boundary. So the augmentation is, since there are two CAs and an EngramNCA, one of them can be allowed to be toroidal and one of them can be allowed to be non-toroidal. And they can sort of exchange information by encoding it in their hidden channels. So for problems where toroidal behavior is good, then the one that has the toroidal information sort of gets priority. Or, I mean, I say this is all implicit in the training. Whereas for non-toroidal problems, the one that has non-toroidal information gets priority. And the non-toroidalness is just padding is all zeros. There's just a hard boundary around the problem. And then the local versus global, we have the regular training on the entire grid. But you can also do something called patch training. So that is, you can decompose the grid into 3x3 patches, very local patches with very local information. So there's information can't propagate more than one tile. And you can train it on those patches. So you can take a patch and say, all right, do n update steps on just this local information you have on a 3x3 patch of the problem. And then compare it to what a 3x3 patch of the solution to that problem would look like to sort of enhance local information propagation. We also added channel-wise attention to each cell. So each cell could sort of attend to its own channels. These are the RGB alpha hidden channels and gene channels, but not to any of its neighbors, just its own channels. Another thing we had to do was from ARC to NCA. So like I said, they're 2D integer grids with 10 states. We chose to represent the ARC problems as RGB images. So what we did was we took the integers 0 to 9 and we mapped them onto an HSL wheel, equidistant on the HSL wheel. And then from HSL, you can map to RGB alpha quite easily. And then, so you get an RGB alpha output, and then that can be the first 4 channels of the NCA. The other channels were filled with different representations of the ARC problem. So we also sort of added a binary encoding of the integer state of the cell in the ARC. So if it was 0, it'd get 0, 0, 0. If it was 1, it'd get 1, 0, 0, so on and so forth. Or 0, 0, 1, sorry. And then some other ones, I forget exactly, but there are basically some extra encodings that we hand put into the NCA's initial starting grid. There's also dealing with changing grid sizes. So ARC problems, they can have different output sizes than their input. NCAs can't really modify the size of their own grid. So the first experiments, we just ignored those problems. And then the second ones, we just padded all the problems to a maximum size of 32 by 32, and then used a special padding token, in this case -1, to pad the borders. And so the NCA could modify that padding token, and then it's just a crop to fit to get the output size. This can be seen as a program synthesis approach. So we consider each NCA as a new program. The NCA training loop is the program generator. And then for each problem, we generate a new NCA from scratch, training it only on the examples given. So each problem that you see solved in here will be a new NCA that has been trained on only the 3 training problems and then evaluated on the evaluation problem. The training loop, so this is what I was saying before, is the same as the gene prop CA, except the gene CA is not frozen. It is also started randomly and trained in tandem with the gene prop CA from the start. So they sort of co-evolve together. I can go on later if you want as to why this was done, but effectively here you start with 2 CAs from scratch, gene CA and gene prop CA, completely random networks, and you train them both at the same time. So they become codependent on each other. Yeah, some general notes on the results. They effectively display this sort of growing, almost organic look to them. I think it's pretty neat to look at. Let's restart. Yeah, that was.
So maybe Etienne, before you go on, so just
Yep.
a quick question. ARC-NCA 1, should we just give a quick sort of idea of what the problems look like, just to get yeah, okay, maybe. So maybe if you go back to the kind of image with a few problems.
This one?
Yeah, for example, so you get a few input grids, and the goal is to generate a single output, or you have actually two attempts. That is a full-size image. That is the correct image to the problem. For example,
Actually,
in the
I have a
one
better
on the
slide for this.
oh yeah.
This here, you can see some of the inputs problems.
Yeah. All right. So in this case, you can intuitively, as a human, grasp the nature of the problem. In the first one on the top left, you have some dots and a couple of solution examples that you have in the line below. You see that the dots that are on the same line or on the same column, they have to be connected by basically a purple line, and those that are just not that are single points on that x y coordinate, they remain as they are. So typically systems, they produce in a single shot an image or an output solution that is the correct one. Here, what is the trick here? The trick is that we are growing the solutions developmentally. And this is beneficial for a lot of these kind of problems, because while it is difficult to generate in one shot, you can, in this case, for example, you can let the dots grow their own lines and columns, and if they don't collide with anything else, they will retract, for example. But if they collide with something, they will basically become stable. So it's a behavior that it's much easier to learn in a incremental way, in a developmental manner. In the one below, for example, in the one in the center below, here you have some lines of different colors, and you have to grow, you have to fill basically the space that is enclosed within the shapes. The one outside is in different color, it's in a kind of in the green color, and the one inside is in this yellow color. So here you can grow, and if it basically touches something, some border, then it can learn to basically stay there. And then if it's outside and it touches some kind of border, then it will actually have to retract and kind of and be of another color. So this kind of idea is that it shouldn't be possible to solve these problems with a couple of examples, training those two NCAs, but the fact that it's a combination of this developmental process, number one, so it's kind of incremental, step by step, it can grow, and the second one is that it's kind of local. So it's like I think those are the two main aspects here that allow these tiny NCAs to solve these kind of problems. That they are like
I would add a third thing, which is the pooling method. So I never explained this, but this is effectively a slice of the pool over time. Starting grid. As you update the pool, some of them stay as starting grid, some of them stay as intermediate updates. Obviously, as the pool goes on, it gets better and better as you get better results. But effectively, the CA has to learn to recover from sort of terrible positions. Like, if I could pause this at the right time. Yeah, sort of terrible positions like this one or this one. This happens as well for ARC-NCA. And to be able to recover from this, you are creating global attractors and effectively saying for anywhere in the state space that we want to collapse to this single state. And I guess for that to happen on ARC problems, it has to learn very general rules, or else you're not collapsing to a single state from very irrecoverable sort of jumbled states.
Yeah, maybe I should add also that if you are familiar with the new growing neural CA, the initial version, so in the beginning you have like a single seed that is then forced to grow into a certain morphology, let's say the gecko or the smile, and if you just have that kind of target shape in your pool, it learns over a certain number of developmental steps to grow that, but after that moment it kind of degenerates. It doesn't learn anything beyond that point. However, this can be solved with the trick that you basically, if you want to keep it stable after that, you can put the target morphology back in the training pool, then in fact replacing part of the pool of the initial seed cells with the final morphology, so that it learns from that morphology to stay in that morphology. So that's a kind of a trick one. Also, you can learn to basically make it robust to damage. And to do that is another trick with the pooling. Basically, once you grow that morphology, then you can damage it, basically add some random noise or remove a chunk from it, and put that damaged part back in the training pool so that it learn to regenerate the target shape from it. So with these tricks, you can basically, recover, and this is very beneficial for the ARC, because if it grows something that is a little bit wrong, but then it can sort of learn to correct it. So it can learn strategies that grow and overshoot, and then maybe kind of find the kind of the target solution. So I think this is very beneficial.
Yeah. All right. So that was the solved problems. Stefano actually described exactly what I was going to say for this. So thank you. Yeah. On the results, the mean log loss was basically just a pixel-wise loss on all of the ARC problems that we tested, whilst the solve rate is any individual problem that had a log loss of -7. This is log base 10. Oh no, sorry, natural log of -7 or lower. The reason for this is because of the HSL RGB mapping. You actually have some leeway in the colors, so you don't have to have the exact same color as the ARC problem in RGB space, since once you map back to an integer, you clip to the bottom, or you basically clip to the floor, and so you have a leeway. You have about 10% wiggle room on each side for the clipping, with 10 different states, effectively. Or not 10%. No, actually, yeah. About 5% on each side. So our results were for the standard NCA. I'll just highlight the more important ones. Our standard EngramNCA actually performed worse than the standard NCA. However, Engram V3, so this is the one that had toroidal and non-toroidal, which is an advantage given to us by the fact that there's two CAs instead of just one, performed the best at 13% solve rates on all the problems. As a little point of comparison, ChatGPT 4.5 has a solve rate of 10.3, so actually the same as EngramNCA V4. If you take the union, so again we get two shots at the problem. So what you could do is take two different NCAs and take their unions, or i.e., which problems they've managed to solve combined, and that can give you your effective two-shot rate, since you could just run both NCAs as one for each shot, and it will accept the better answer. And in terms of union, our best one was V1, so this is actually just standard NCA. EngramNCA, and V3. So this is the one that's augmented with toroidal information. And so what this sort of tells us is that even though the V1 had the worst score, what it managed to solve were different class of problems than the V3. And so when you take the union of them, they have the least overlap. We move on to partial solutions.
May I just a quick those may seem terrible results to those people used to like 99.7% scores or something, but basically until recently, ChatGPT 4.5 was the state of the art model. Around 10% was quite a lot. Other methods are like around 2-3%, but then it was a big gap when chain of thought models, so basically allowed to reason for longer and generate their internal kind of reasoning tokens, came out. And then with those, there was a big gap and a big jump in performance. But so we chose also as a kind of a reference ChatGPT 4.5 because it doesn't have chain of thought reasoning as a comparison. Those other reasoning models, they can basically go on for as long as one wants to kind of produce intermediate solutions and think for very long, like days or like hours or something. And so we didn't think it was a good comparison. But yeah, so I just wanted to say that it's not a fair comparison with ChatGPT 4.5 anyways, because we haven't tested the actual private evaluation test. We tried on the basically the training and the public one, but I think it doesn't really matter because we don't really do any sort of pre-training. We don't capitalize on pre-training. Try to learn something from one problem to generalize on another. We just retrain every time. So I think this doesn't matter. And those problems are also built in a way that it should be very difficult, or there should be little to learn from one problem to generalize and try to apply the same solution to another problem.
Yeah. Also, so the training set for ARC-1 is almost there to try and give your system the priors for helping it on the private evaluation sets. In a way, they're almost like if you can learn the priors from that, then it could help you. So if you're doing pretty well on the training set, then you're probably learning the correct priors. Yeah, also just to add to what Stefano said, so ChatGPT 4.5 does it in one shot, whereas the reasoning ones can reason for as long as they want, and the ones that get good scores reason for so long that their costs are in the hundreds, if not thousands per task. We limit our growth time to 132 steps of the NCA. So it's you could see it as if you unrolled the network, you could see it as almost a mapping in one shot. You would just have to unroll it for 132 steps. Anyways, onto the partial solutions. So a lot of them, we actually had partial solutions that are quite close. On the left, we have an example of just sort of an unseen scenario, an edge case that it didn't train very well on, which was this sort of large 2x2 gap in the corner, or basically large gaps here in cross sections that weren't very present in the training examples, and so it struggled. And on the right here, what we have is a solution that actually passes through the exact solution. So here's the exact solution that you want. And then sort of overshoots it slightly. So instability at the point where it's supposed to like decide that it should stop growing. So we decided to check what would happen if we loosened the solve rate. So this is instead of a log loss of -7, a log loss of -6 was sort of the region where you had a lot of problems that were very close to actually being a full solution, but were just slightly off. Standard NCA gets about 15%. Again, V1 is still the worst. And V4 at this point now becomes the best at about 16% solve rate. And their unions, the best one is V3 and V4. So they have the most partially solved ones that don't overlap. And what this tells us is there's actually quite a lot of margin. So we went from a 12% to 16% solve rates if you just loosened it, which means there's a generally or like a sort of like a 4% window of you're really close to actually solving it. You might just need a little bit of compute, and I'll get to that in a minute. We also looked at the costs. So these are actually quite conservative cost measures. When I was doing this, I lived in the Netherlands, which is a very expensive country for electricity compared to the US. I took the electrical costs in winter, so the worst time to take electrical costs. And I basically took the average cost to train the entire, so per problem, the average cost to train the entire data set. And we had a training cost of in the e to the -4, or basically 10 to the -4 dollars. This was converted from euros to dollars per task. So we're talking fractions of a cent per task. ChatGPT 4.5 takes about 29 cents per task. If you look at the better reasoning models, or 3, or 1, stuff like that, they're like in the hundreds. So they're very expensive, whereas this method is actually really cheap. Again, it was done on a 4070 Ti at home in my bedroom. It takes about, especially for the smaller ones like NCA and EngramNCA V1 that take less computation, it takes less than a day to train the entire data set. So the cost for NCA is the training plus inference, whereas the cost for the ChatGPT is just inference. This does not take into account the fact that it was pre-trained for, I don't know, $50 million. And NCA inference time only is vastly cheaper than training plus inference. So we're talking, I think, 100 to 1,000 times cheaper. So training, say, a single problem takes about 10 gigabytes of VRAM. Inference is about like 200 megabytes. And it happens a lot faster as well, because in the training, you have exponential growth with the size of the grid, so the height and the width of it, and linear growth with the time you run. In terms of cost, because you're having to record gradients for all of that. Whereas in forward pass, you don't record any gradients. It's just fully local interactions. So it's really just the cost of running the grid without any gradients. The final piece of results we got were reasoning pitfalls. So these were problems where sort of one of the reasoning steps was correct, but the second one wasn't. As you can see in the inputs here, the idea is basically you get this shape on the left, and you have to grow it on the dots on the right. And the dots change in place, so it didn't just memorize where to grow a square for the actual validation problem. So it learns that it has to grow a shape on the dots, but it doesn't learn exactly what shape. This is mostly an issue of long-range communication. There's a lot of information that has to be passed from here all the way to here locally, exactly, to replicate this shape. And it is often easier to then just memorize these shapes. And if you actually look at it, this one here is a memorization of this one here. And these are most probably just jumbles of the other training outputs. So you can get partial reasoning, which is quite nice. And how to fix this, I might talk about it later. Some further experiments, we also just took the CAs and we just threw more computation at them. What if you make them bigger? So we took EngramNCA V3. This is the sensing plus toroidal, and then the V3 we just did maximal padding as well. So this was padding all the problems so that they had a hard boundary that they can modify, so we could test it on all 400 ARC problems. And the solve rate was 16% for both of them. So padding didn't actually change, seemed to affect the solve rate. You probably lost some problems with the padding, but then gained some problems with the padding. And it gets to about 16%. 16%. If you just take the partially solved solutions, you can go all the way up to 27%, which is really good. And the training costs went up to, for the non-padded version, 5e to -4. For the padded version, it's obviously higher because you're using larger grids since you're padding them, all of them, to a maximal size. But it's still in the e to the -4, so fractions of a cent instead of fractions of a dollar. I also wanted to talk about some parallel work that was published after ours, about 2 months after ours, which I thought they touched on a very neat thing that we didn't talk about, but I think it's very relevant. This is neurocellular automatons for ARC-AGI. They effectively did a very similar method to us. Their encodings of the problems were different. However, their results were the same. They have about the same solve rate as us for a standard NCA. They only use the standard NCA. This is by Risto and Mikulainen. So very similar results for standard NCA, which sort of shows that ours wasn't a fluke. Slightly different method. They did a more in-depth analysis of generalization, however. So they took this one, this problem here, the spiral, which was also one that ours solved without problems. And they said, what if we just make the grid instead of 13 by 13 or 15 by 15, 100 by 100? Does it keep generalizing? And the answer was yes. As for the same class of problems, it just, if you had a solution on the validation example, then you had a solution for any problem in that class. If the problem was, say, grow a stick from a dot, it doesn't matter how long that stick would have to be. If the problem was make a spiral inside a grid, it doesn't matter how big the spiral is, which is quite remarkable because to find a program that could do this would actually take a lot of compute. And some discussion. So solve rates, about 10 to 15% baseline, padded versions improve partially. It's extremely low compute. Can be done at home, basically. The partial solutions indicate a promising avenue for improvement, which is effectively this. We threw more compute and it solved 16%. And if you look at the partial solutions without more compute, it's about 16%. So for some problems, throwing more compute did actually just solve those ones that were very close. This has a limit, though. I did try with even more compute, and it didn't go past 16%. NCAs excel at iterative refinement and emergent reasoning. However, they struggle with fine-grained details, novel edge cases, and long-range communication. A little bit of critique, since our papers actually got into a conference, so we did get some critique. We used a public evaluation set. This is what Stefano said. risking unintentional bias. I don't think there's any risk of unintentional bias since we are doing effectively program synthesis, starting from scratch every time. But this does mean it is hard to compare. It's effectively on a different benchmark to ChatGPT. And the current approach trains a new NCA per problem. Impressive for few shot solving, but unclear if this supports reasoning to novel tasks. Again, we can solve to same task of the same problem, so the same sort of computational regime, but you wouldn't be able to solve anything outside of just making a spiral once you have the NCA spiral. A little bit on what next. The approach is effectively canonical. Would be the simplest way, I think, to solve ARC using an NCA. Just ARCs are a grid, NCAs are a grid. Pretend the ARC grid is the NCA and let it evolve over time. So there could be some improvements. One on pre-training the NCA to develop priors, especially human-centric priors, would actually help a lot. Methods that combine NCAs for reasoning and image processing seem promising. So this is by a colleague of Stefano's group, where the NCA acts as the neocortex. It's a smaller NCA than the image that it's trying to process, and it's allowed to move a sensor, effectively the convolution filter, at will. So it doesn't just convolve over the image, but it can choose where to look. And what was nice about it, it has sort of emergent attention, where it would choose to focus its attention on specific parts of the image, and then the NCA, which was the processing logic part, then would give you the classification of the image, and also tell you where to move the sensor. Another one would be critical NCAs in neocortex. This is to solve the long-range communication issue. NCAs at a critical state effectively have long-range communication capabilities, and so you might be able to solve more of the problems that require long-range communication. Anyway, thank you for listening. Any questions? I see there's something in the chat.
Yeah, thank you so much. That was super interesting. I have one question, especially on like some of the linear shapes that you saw. Do you think it's possible to use these kind of approaches to detect one thing that's still problematic is looking at a data set of patterns within some excitable medium. Maybe it's our bioelectric networks, maybe it's transcriptional networks, whatever, and identify some kind of coherent subsystem that seems to be doing something interesting. And so I mean, our visual system does it very, very easily, but some kind of a way to use this to actually find what are the agents in your data set. Do you know what I mean?
Oh, yeah. So I actually went to a conference recently called Detection of Emergence and Complexity, and specifically focused on this.
Okay.
A lot of it was basically saying all the measures we currently have effectively boil down to homograph complexity, and so it's very hard. The only way I could see this actually being used would be to almost use the size of the NCA needed to encode different scales of activity as a measure of the complexity of that activity. So if it's something that's very simple, in theory, you need a tiny NCA to sort of replicate the video of that very simple thing. Where if the activity becomes quite complex, you're going to need, and as it becomes like almost like critically complex or arbitrarily complex, you need an NCA of arbitrary size. It just gets more and more expensive. So you can almost see it as like if you have a dynamical system and you want to see if any of the parts are like complex behavior that could be interesting, you try and get the NCA to simulate it, and you see what size of an NCA you really need.
Got it. Yeah, that's quite interesting. Thank you.
If I can comment, it's a very cool question. And another thought that we had is a kind of a combination of this method that we have discussed with this kind of gene propagation and gene growth interacting with each other. Also with this kind of methods for basically compressors, so autoencoders, kind of embodied autoencoders. Embodied autoencoder. So there you could learn in a way, I don't know if I would call them agents, but you would learn to compress whatever you have to the minimum information needed to regrow it. So that could be a way to kind of identify the important features in the system. But of course, it's a very tough question. This one about like how do you sort of identify the agents in the system and how how to coarse grain it to the right in the right manner to kind of remove whatever is like noise or irrelevant and just have the important features. Yeah, it would be nice to brainstorm more on that, definitely. And yeah, of course, we have tried a bunch of like coarse graining methods. And autoencoders are one machine learning based, but also we tried like a kind of a frequency based, basically statistical methods where you just patch your image and you collect statistics of the different neighborhoods that you have, and then you make some kind of a histogram, and basically then you set a threshold, and whatever is above or below, it's kind of kept or removed, so that you kind of basically do this kind of statistical sort of a coarse graining on that. Ultimately, it would be very nice to be able to detect kind of. So if I can open a parenthesis, I'm always fascinated about this video where you have a game of life inside the game of life inside the game of life on multiple scales. So it would be wonderful to kind of have a sort of a way to measure a kind of the complexity at one level and being able to kind of match the complexity at the next level. A way to kind of measure and have the same kind of measurement at different scales. So yeah.
Can I ask another question?
Thank you.
Yeah.
So I just wondering, is this neurocellular automata inversible? Like because you are training it from a single cell, and if I given this neurocellular automata a pattern and reversely running the neurocellular automata, would it grow back to a single cell so you can do some kind of pattern decomposition?
I mean, not implicitly, no, like you can't train a neurocellular automata to grow from a cell and then run it in reverse. This is also just down to uh, uh I forget what this how to say this exactly. Um so systems that are as complex as a neurocellular automatas, they eventually reach a state where you actually can't reverse it. So if you look at this, it grows a square, right?
Yeah.
And then it stays there, and you can run this for an infinite amount of time, and the square stays there. So you
Oh,
never know what state you just came from once you're at the square. So you wouldn't actually be able to reverse it, like because you could have come from the
yeah.
previous state, or you could have just been on square for a million years. Yeah,
Oh yeah. You're already in a limit cycle, so you don't know
yeah,
where you're from.
exactly. Yeah.
So
Now you could
you
probably
could
train a neurocellular automata to just reverse a square back into the original seed cell.
yeah, that's what I was thinking. You could basically learn both processes, try to kind of grow from a seed to a shape and from a shape to a seed, and then it will basically have a kind of learn a kind of a tractor to go back and forth. Probably it's kind of a nice thing to try out, maybe to make it reversible, to train it to grow a shape, and from that shape train again to go back to the original initial cell and see if it learns kind of to bounce back, and it learns this kind of repeating attractor. That's a nice thing to try, maybe.
Hey, can I ask a question?
Yeah, of course.
Really cool work. I'm surprised that you were able to solve some of the tasks with just the examples without augmenting it in any way. So really impressive. I was just wondering about your failure cases. You showed me, I think you had one slide on some of the partial solutions. Probably one failure case that you described.
Yeah.
I just wanted to ask, did you try any other, like, did you have an analysis of what went wrong? What were the things which didn't work? The problems for which this approach didn't work?
Not in the paper, but internally, yes. I spent a lot of time looking at the problems. Yeah, a lot of them came down to long-range information communication. So like this one. Another one was, say, basically you had a central dot and then a branch coming out of that central dot, and you had to replicate that branch whilst turning it, basically like creating a floral pattern from that branch around the central dot. That one also would require long-range communication, and then also like transposing or rotating that information you're propagating. Effectively, anything that required long-range communications had difficulties. That was like move a shape like quite some distance. You could argue these require, or this one requires long-range communication, but this can actually be confirmed locally. Like this is the sort of problem that you can sort of almost fully locally confer all the information you need, where you just check if the cell next to you has some sort of activation. And if it does, then you have that activation, and then your neighbor will check if you have that activation, and this can propagate. Whereas something like this, this is less about propagation, some level of activation to tell you about the state, and more about like moving a whole shape. And that is, it can be done. There is one problem where it does move the shape, but it doesn't move it a long distance. It's maybe like 3 pixels. But for
Yeah.
longer things, yeah.
No, I think the long range thing you have it set because you grow a lot of complex things. I doubt it's a long range problem. It probably more has to do with symmetry, you know. I don't know if you've checked the tasks which explicitly involve symmetry. This is one for sure.
Yeah. So the ones that explicitly involve symmetry can be hard. It just depends. So this one on the right, I mean, this one's more like actually just growing NCAs. This one is perfect for NCAs. It is just growing from seed cells. But this one involves a sort of symmetry or like a reflection above a line. Yeah, I think it's also down to the complexity of that symmetry. So like with the floral pattern one that I was saying, it requires both the transposition of the pattern and the rotation of the pattern. And so it can be quite difficult to both convey the pattern and also the transform that needs to be done to it.
It would really help if you could do an analysis of some sort about what kind of problems work and what wouldn't. It would probably be a big thing to help others.
This paper has a good analysis on the problems.
I did take a look at this. Yes, it's quite interesting.
Yeah, a more detailed. I mean, I would agree. A more detailed, like almost go problem by problem and see what's happening. Could indeed help.
One last question. Have you tried training 2 or more tasks or 2 or more problems with a single, I mean?
With a single NCA. Okay. Well, we did try basically pre-training an NCA on a lot of the problems, and then seeing if it was any good at solving all the other ones. But again, a lot of the tasks don't transfer. I haven't tried just taking one that's say like good at growing, something like this, and then trying to use it and using it as like the starting point to train on another one. But that actually is an interesting idea where you try and use it already trained on one task and then just retrain it on something else. And it's probably quite close already on a lot of the problems.
I think what goes wrong would be very interesting. Or why doesn't it grow? An analysis of sort would be quite interesting.
Yeah. I think another idea we had was to pre-train an NCA on very basic pixel-wise primitives, like move a pixel, delete a pixel, recolor a pixel, stuff like that, just so it has the tools, especially the GNCA, because that's the GNCA's effectively its role in this is just to draw the ARC problem, and it's more to the gene prop CA that does the reasoning by moving the genes. So if we could effectively condition the gene CA on some genes that tell it, hey, if you see this, delete. If you see this, move to the right, move to the left, all of this. Then you have almost these logical primitives that the CA can use. And then you would just have to train the gene prop CA to like move or basically activate those primitives at the right time or at the right place during the growth process.
Yeah, I mean, probably one thing you could use is you have the original program synthesis solution where you have the guy who's written explicit programs for each of these primitives. You probably use some ideas from them.
Yeah.
Thanks.
Any
Yeah,
other questions?
super nice work and talk. So maybe I can ask regarding my previous question, why you trained this in tandem, or what was the benefit of training them both at once?
Yeah, so yeah. The training in tandem was basically an issue of we do not know. So the gene CA is trained on to be conditioned on the genes, right?
Mhm.
The issue with the gene condition is you have to know prior what you want to condition on. And with ARC, sort of the whole problem of it is it's really hard to know prior what you have to condition on. So you could pre-train on a lot of the ARC problems, and each ARC problem could get a gene encoding, or you could pre-train on uh, uh, like just different variations of this, but it was all very ineffective. So the idea was if you can't know what you're going to condition on, maybe just try and learn the conditioning and the conditioner at the same time.
Yeah, that makes
And
perfect
that
sense.
was yeah, and that was the most effective, to be honest, since
Mhm.
it was impossible to know what you had to condition the gene CA on. So yeah, that's why.
Super nice.
And so this sort of
Uh,
answers your previous question. Can you do it? Yes, yes, you can actually. And maybe it actually
you
learns
should.
better. Yeah, yeah, you probably should actually. Yeah, it learns better encodings. But with, say, with the EngramNCA, what we were showing here, it would be very difficult to uh, pre-train this behavior when you're training them in tandem, because this is the gene CA has never seen the gene prop CA. This is just the gene CA doing its own thing. And then the
Mhm.
gene prop CA grows the lizard. But if you were to just grow the lizard, then yeah, it's probably just better to train them together. This is just showing uh, you can train behavior and then you can exploit that behavior to do more complex tasks.
Yeah, that sounds reasonable. It's like two different problem classes. One is growing and the other one is kind of refining, right? I mean, kind of related, but
Yeah,
yeah,
yeah, yeah.
something to
So
think
yeah,
about. Yeah, and one last question, maybe because Lecturer asked a question about pre-training the NCA stuff. You also worked on critical NCAs, right, in your group. So did you try using critical NCAs as starting conditions, or did you use
yes.
randomly initialized ones?
So I did actually try on critical NCAs as a starting condition. Um, Again, the issue becomes, especially with okay, a little bit of background. So I actually did my master's thesis on training critical NCAs for like running them on the cartpole problem. Um, and the nice thing about the cartpole problem is that you have cells that are input cells. So the NCA was trained to be critical in relation to like certain channels where the input would be. Um, uh, so you can sort of do the same thing with this. So you train the NCA to be critical at certain channels. And then for the output channels not to be, especially with with the EngramNCA, you just train the Dream Prop CA to be critical. So that's the one that's doing all the information propagation. Uh, Two problems that would arise is at the start of training, uh, basically you could have like runaway sort of explosive behavior that would poison the pool since it's very sensitive. Especially the larger the critical NCA in terms of parameters, the sort of almost the more sensitive they become. Um, uh, yeah, so that was the first problem. And the second problem is back to what do you condition on? Like, so yeah, the gene prop CA channels are critical, but um, they get such a vast array of different information that you sort of just want them. Yeah, I don't know how to explain this. They it's sort of it's not conditioning agnostic in a way. Like, yeah, it's critical. It expands the information everywhere. It's maximally computing, but it sort of jumbles the information a bit too much for ARC, in a way.
Mhm. I see.
Um, Especially for a lot of the problems, as you can see, like up here, you like you really don't have to be critical. You just have to propagate linearly in a lot of these. So it I would say if you are going to use critical NCAs, then you have to change the approach from dealing with the image itself to the NCA actually being the neocortex, the part that does reasoning, and for it to just produce the output in a different way. So what I was almost saying here, where you have like a sensor and it can look over the image, and then the NCA does the reasoning part as like sort of like a thinking machine, almost like how you use a standard neural network in a way of just like you encode the input, it does a bunch of mapping, a bunch of thinking, and then it gives you an output. You would have to use the NCA in almost a very similar way, instead of it just acting directly on the grid, if you want to use a critical NCA.
Mm-hmm. Yeah, thank you.
Anyone have any other questions? Okay. Thank you. That was amazing. I was really amazed to see that the ARC-NCA is have a good start of a success rate. That's amazing, especially with NCAs. Thank you, and I'm sure that people will send you more emails with more questions.